Hello everyone, this is the problem solving video for lecture 4 of EEE 41, where we'll discuss some problems related to carrier scattering, drift, and resistivity. So some formulas that we'll use or we might use in this section. So we have already derived or shown the equation for the drift current densities. So these are current densities for drift of electrons and holes. So this is in some amperes per cubic or per square centimeters. For electrons, we have Q, N, mu, and E. And for holes, Q, mu, P, QP, mu, P, E. Where mu is the mobility. We can actually sum the two and get the total drift current density, and that is equal to sigma E, where sigma now would be equal to Q mu N times N plus Q mu P times P, and the reciprocal of the conductivity is resistivity. So resistivity rho is 1 over Q mu N plus Q mu P P, and the resistance of a semiconductor is rho L over A. Now this table here is also provided for a quick reference. So these values are valid for silicon at room temperature. So when the material is not silicon, or silicon but is not in room temperature, then we will not, or these values are not the correct ones. Okay, so for the first problem, we have a doped crystalline silicon with a length of 32 nanometers and the cross-sectional area of 64 nanometers by 64 nanometers, and this rectangular prism will be used as a resistor. The semiconductor has a relatively light doping of Na is equal to 5 times 10 to the 16, so it is a p-type semiconductor. So questions are, what is the length in centimeters? What is the cross-sectional area in centimeters squared? What is the resistivity of the semiconductor at thermal equilibrium at room temperature? And then lastly, what is the resistance of the semiconductor at thermal equilibrium at room temperature? So again, we just summarize some details from the given. We have silicon, length is 32 nanometers, which is 32 times 10 to the minus 9 meters. And then the area is 64 nanometers by 64 nanometers, or 64 times 10 to the minus 9 meters times 64 times 10 to the minus 9 meters. And the acceptor doping concentration is 5 times 10 to the 16. So we convert the length in centimeters by multiplying 32 times 10 raised to minus 9 meters by 100 meters per 1 meter to cancel the meter. So basically we're multiplying by 100. So the length in centimeters is 32 times 10 raised to minus 7. So from minus 9 to minus 7. Next, the cross-sectional area in centimeters. So we have 64 times 10 to the minus 9 meters squared. We multiply by 100 centimeters per 1 meters squared to cancel the meters squared and be left with cm squared. So we have 64 squared times 10 to the minus 9 squared, which is 10 times 10 raised to minus 18, and 100 squared is 10 raised to 4. So we'll actually get 4.096 times 10 raised to minus 11 in centimeters squared for the area. So we'll be using these two values for length and area. So we now have written the length and area in cm and cm squared respectively. the next question, what is the resistivity at thermal equilibrium at room temperature? So the formula for resistivity is 1 over Q mu Nn plus mu Pp. Why do we need the information that it is in thermal equilibrium? So that we can compute we can determine N and P. And we also need the room temperature to determine its value. Now, some of the components. So P first. So P is approximately equal to Na, which is 5 times 10 to the 16. Now note that Na, which is 5 times 10 raised to the 16, is much greater than 10 to the 10. So we can just proceed with P is approximately Na. Now for N, we can use the law of mass action and use 10 raised to 10 over Na, which is 5 times 10 raised to the 16, and get that N is 2 times 10 raised to 3. So we note here that N is actually very small relative to P. So 10 raised to 3 versus 10 raised to 16. So we already have the values for N and P. The next is mobility. So the table for mobility is, or the values for mobility for the doping of 5 times 10 raised to the 16 is included here for our use. And then Q is just a constant, 1.6 times 10 raised to minus 19. So we can now actually use those values in the formula. So 1 over 1.6 times 10 raised to minus 19 times 986 times 2 raised to the 13. So note that mu n and mu p are different. So mu n is 986. So next, mu p is 378 multiplied by p, which is 5 times 10 raised to the 16. And with our calculator, we should be able to get this value, 330.7 times 10 raised to minus 3. And our units for resistivity is ohm centimeters. Now we can actually use a shorter solution. So since n is much less than p, we can actually remove the mu and n term and just use 1 over q mu pp. And the answers are close enough, and we'll just get the same value, 330.7 times 10 raised to minus 3 ohm centimeters. So the question for this problem is, what is now the resistance? So from resistivity, we are to compute the resistance. We already have the resistivity. So R is equal to simply rho L over A, where rho is 330.7 times 10 raised to minus 3 in ohm centimeters. And now we'll use the length and area in cm and cm squared. So we already have those values, and using our calculator, we should be able to get that the resistance is 25.836 kilo ohms. Okay. So in summary, for the first problem, we converted the length from nanometers to meters or centimeters by multiplying first by times 10 raised to minus 9, then for the nanometers, and then multiply by 100 to convert from meters to centimeters. For the cross-sectional area, we multiply by 100 squared and get this value. Now for the resistivity, the dimension does not matter first. So we computed first the N and P, then determine from the table the value of mu N and mu P to be able to solve the resistivity. Now, given the resistivity, we use the dimensions to compute the resistance. For the second problem, we have a silicon bar, which is from the previous problem, so we will use the same dimensions. But now it is fully compensated by adding donor dopants of 5 times 10 raised to the 16. So note that previously we have Na is equal to 5 times 10 raised to the 16. But now, in addition to that, we have Nd is exactly equal to 5 times 10 raised to the 16. So that is what we call full compensation. Assume that the material is still in thermal equilibrium and at room temperature. So we are now asked, what is the resistivity of the compensated sample? And then what is the resistance of the compensated sample? So that is after adding Nd equal to Na. So looking back, we computed the resistivity as 1 over Q mu Nn plus mu Pp. We already know Q, but now what is N and P? If we have a fully compensated semiconductor. So since Na is equal to Nd, then the fully compensated semiconductor simply acts like an intrinsic semiconductor, where N is equal to P is equal to Ni. And how do we prove that? Since Na is equal to Nd, then Na minus Nd must be equal to 0. And we'll be left with the square root of Ni squared, which is simply Ni. And this is actually this equation. So N is equal to P is equal to 10 raised to 10, since we have silicon at room temperature. So we add this information here and still answer what is the resistivity. So aside from N and P, we also need the mobility. However, the mobility depends on the total doping concentration. So the total doping concentration is Na plus Nd. So since Na is equal to Nd is equal to 5 times 10 raised to the 16, then Na plus Nd must be equal to 10 raised to 17. And therefore, we must use 801 for mu n and 331 for mu p. However, since n is equal to p is equal to ni, then replace this with ni, then factor out ni, which is 10 to the 10, and we'll be left with q, which is 1.6 times 10 raised to minus 19. Now inside the brackets, we're just left with mu n plus mu p, which is 801 plus 331. Then we've factored out ni, which is 10 raised to the 10. So we can compute the resistivity as 552.1 times 10 raised to 3 ohm centimeters. And we just note that we have a drastic increase in resistivity. So from the previous problem, the resistivity was 330.7 times 10 raised to minus 3. but now it is something raised to 10 raised to 3. The resistivity increased because since we compensated the material, there is a big decrease in the carrier concentration. So note that from P is equal to 5 times 10 raised to the 16, it just became 10 raised to 10 since we fully compensated the material. So with only few carriers available, then the resistivity will be higher or increase. So we note that our new resistivity value for the compensated material and proceed with computing the resistance, which is given by simply rho L over A. So the dimensions did not change, but the resistivity changed. And so since the resistivity increased, then the resistance must increase. So here we note that for this dimension, for a fully compensated material, semiconductor at room temperature, at thermal equilibrium, then we can get something at 43.13 gigaohms. So in summary, we were able to compute the resistivity, but note that we used for the compensated sample that N is equal to P is equal to Ni, and then the mobility is a function of Na plus Nd. So aside from N and P changing to Ni, the mobility values also changed. For the resistivity, the dimensions did not change, but since the resistivity changed, then the resistance must change as well. Resistivity increased, so the resistance must also increase for the same dimensions. For the third problem, we have a crystalline silicon. Given Nd is 10 raised to the 14. We are given the length already in centimeters and the cross-sectional area already in cm squared. Now, a voltage of 0.5 volts was applied across its length at room temperature. So note that we have a rectangular slab. So the questions are, what is the resistivity? Determine the electron and hole drift current densities. So this one is rho, while this one is Jn and Jp, since we are asked with current density. And third, calculate the total current through the semiconductor. So this is not current density, but total current. So this must be some I. So first, what is the resistivity of the sample? We need to know the carrier concentrations and the mobility values. Since we are given just NDs 10 raised to the 14, then we can extract the values for the mobility for a doping concentration of 10 raised to the 14. And since this is an N-type, we can approximate the resistivity as 1 over q mu n raised to n, 1 over q mu n n. Sorry, we were able, we can proceed with this assumption since ND is much greater than Ni. So if it is an N-type but ND is much less than Ni, then we cannot use this approximation. But since ND is 10 raised to the 14, then let's say we'll proceed with the approximation. So Q is 1.6 times 10 raised to the 19. Since it is N-type, the partner of N is mu N, which is 1358. And N is approximately Nd, since Nd is much greater than Ni. So we must be able to solve the resistivity to be equal to 46.02 centimeters. And we have added that information at the top of the slide. And then we now proceed to determining Jn and Jp drift. So first, we have this formula for the drift electron current density. So we already know Q to be 1.6 times 10 raised to the minus 19. Mu n is simply 1358. Now n, we can approximate that to just be equal to 10 raised to the 14 since Nd is much greater than Ni. Now the voltage is 0.5 over the length in centimeters, which is 10 raised to minus 5. So we can already compute the electron drift current density and get this value 1.0864 kiloamperes per centimeter squared. So the next is for the holes. What would change would be mu p. So still Nd is 10 raised to the 14, so we'll use mu p to be 461. We can use the law of mass action to determine p. So by law of mass action, we have Ni squared, so that's 10 raised to 20 over N, which is approximately Nd. So 10 raised to the 14. The voltage is 0.5 and the length is given 10 raised to minus 5. So we should be able to compute this drift current density for holes. And we'll get the value 3.688 microamperes per cm squared. So note that this is a very small value relative to J and drift, since there are very few holes relative to the electrons, since this is an N-type semiconductor where P is approximately 10 raised to 6. So that is very small relative to N, which is approximately 10 raised to 14. So we note the values we have computed for the current densities. So lastly, we compute the total current. So the total current is just the current density multiplied by the area, but the current density has two components, Jn drift and Jp drift. However, since Jp drift is very small, we can approximate the total current to just be equal to Jn drift times A. So the value of Jn drift is 1.0864 times 10 raised to 3 amperes per cm squared. We multiply that with the area, which is 2 times 10 raised to minus 9, and be able to compute this value. I is equal to 2.1728 microamperes. And with that, we have actually answered all the questions. We computed the resistivity. So for the resistivity, we use N is approximately 10 raised to 14, which is because this Nd is much greater than Ni, and this is silicon at room temperature. We also needed the mobility values to compute this one, so we use the table, and again use Nd is 10 raised to the 14. For the drift current densities, we just use the carrier concentrations. along with the mobility, and now with the addition of the electric field, which is the voltage over length for a uniformly doped semiconductor. So lastly, the total current, we just multiplied the sum of the drift currents, which is just approximately equal to simply Jn drift. We multiply that by the cross-sectional area, so we can get the current through the semiconductor. And that's the end for this practice problem solving video. If you have any questions, just post them on Piazza. Thank you very much.